Okay, tell me if this sounds familiar. You're walking across the room, completely minding my own business. You reach for the doorknob and ZAP.
Oh, yeah.
You get that little jolt of static electricity.
Yeah.
Ever wonder what's really going on there?
It's more than just a minor annoyance, that's for sure. Those tiny sparks you feel are a result of the same fundamental forces that power lightning storms.
Wow.
And even, believe it or not, your smartphone.
Really? Yeah. I had no idea.
It's true.
So today we're taking a deep dive into the fascinating world of static electricity.
Okay.
How do those charges come to be? We'll be unpacking the three main methods of charging: friction, conduction, and induction.
Yeah.
And to help us unravel these mysteries, we have our resident science guru here to break it all down for us.
Happy to be here.
So,
Let's dive in. What many people don't realize is that these charging methods are happening all around us constantly,
yeah,
often in ways we don't even notice.
that's so interesting. So let's start with the classic example of charging by friction. You know that experiment you probably did in school,
Right.
rubbing a balloon on your hair to make it stick to the wall.
A classic for a reason. What's fascinating about that is that it's not the rubbing itself that creates the charge, but rather the transfer of electrons that occurs because of it.
Oh, interesting. So it's like an invisible tug of war happening between the balloon and your hair.
Exactly. You see, every material has a different affinity for those tiny negatively charged particles called electrons.
Okay.
Some materials are like electron magnets, while others not so much. In the case of the balloon and your hair, the balloon is the electron hog pulling electrons away from your hair during the rubbing.
Okay. So the balloon steals some electrons, leaving my hair with a more positive charge, and the balloon becomes negatively charged. Is that what causes my hair to actually stand on end trying to get away from each other?
You got it, like charges repel. So your hair strands are all trying to get as far away from each other as possible. And because that balloon now has a surplus of negative charges, it can then stick to a wall by inducing a slight opposite charge on the wall surface.
So there's actually more to that simple experiment than meets the eye.
Oh, absolutely.
Speaking of electron-grabbing materials, the research we have here mentions another common example: rubbing a plastic ruler with a piece of wool. Same idea, right? Different material, same electron transfer, same static charge.
Precisely. It all boils down to the fact that electrons are constantly on the move,
Right.
and the materials involved dictate how and where those electrons end up. And that, my friend, is the basis of static electricity.
So to sum up,
Yeah.
charging by friction, anytime two materials rub together, there's potential for electron theft.
Yep.
And that's what creates the static charge.
It's as simple and as complex as that.
Wow. Okay, now let's move on to our next method: charging by conduction. This one's a bit more direct, wouldn't you say?
This one's a lot more direct.
Okay.
Yeah.
Let's unpack conduction. This sounds a bit more like what happens when I get that doorknob shock.
Okay.
Am I on the right track?
You are. Conduction involves direct contact between a charged object and a neutral one.
Okay.
Think about it. You're walking across a carpet on a dry day, unknowingly building up a static charge on your body because of, you guessed it, friction between your shoes and the carpet. You reach for the doorknob.
And ZAP. I'm suddenly wishing I had worn those rubber-soled slippers instead.
Exactly. Your body had an excess of electrons thanks to that carpet.
Right.
And touching the metal doorknob gave them a direct path to flow, creating that sudden discharge or shock that we've all experienced.
So that means our bodies are basically walking conductors.
In a way, yes. We're actually pretty good conductors of electricity, especially when we've built up a bit of static charge. That's why it's important to discharge yourself before handling sensitive electronics, by the way.
Oh, good to know. Yeah, I've always wondered about that. So with conduction, it's all about that direct pathway for those electrons to flow from a charged object to a neutral one.
Precisely.
Hmm.
And the research we have here uses a very straightforward example: a charged rod making contact with a metal sphere. The principle is the same. That contact allows for a sudden transfer of electrons, effectively changing the charge of both objects involved.
Okay, that makes sense. So far, we've covered friction, the electron thief, and conduction, the direct approach.
Right.
Now for the sneakiest method of all: charging by induction.
Uh-huh.
This one sounds a bit more mysterious. No touching required.
Right. That's right. Induction is all about influence from a distance. Picture this. You have our trusty negatively charged balloon again, but this time we're holding it near a neutral object. Let's say an empty aluminum can.
Okay, I'm picturing it so even though the balloon isn't actually touching the can, something is still happening.
Exactly. Those electrons in the can, they're not just sitting still, they're constantly moving around. And when they sense the negative charge of the balloon nearby, they get repelled.
So they're like, whoa, too much negativity here. Let's get out of here.
You got it. They can't escape the can entirely, but they can shift within it.
Oh, okay. This creates an uneven distribution of charge within the can, even though no electrons were directly transferred from the balloon.
So one side of the can becomes more negatively charged because the electrons crowded over there, and the other side becomes more positively charged because the electrons ran away. That's wild.
It is pretty wild when you think about it, and that's the essence of induction, influencing the charge of an object without physically touching it.
Wow.
It's all about proximity and that invisible electric field.
Okay, so that explains how the balloon can influence the can from a distance. But in the outline for this deep dive, you mentioned grounding as a way to actually permanently charge something using induction. How does that work?
Great question. Grounding is all about providing a pathway for excess charge to flow to or from the Earth, which we consider to have a neutral charge.
So like a reset button for electrons.
In a way, yes.
Ah.
Now imagine this. We bring that negatively charged rod near our aluminum can again. But this time you touch the can while the rod is close by. Okay, got it. Touching the can while that negatively charged rod is nearby. What happens next?
Because your hand creates a path to the ground, those electrons in the can that are being repelled by the rod have somewhere to escape to. They flow from the can through you and into the ground.
So the electrons make a run for it through me and into the ground, leaving the can with what kind of charge?
A positive one.
Oh, wow.
Even after you remove your hand and the rod, the can remains positively charged because those runaway electrons are still hanging out down in the ground.
Wow, that's pretty sneaky. So grounding is like the secret ingredient that allows induction to create a lasting charge.
Precisely. It's a way to manipulate those invisible forces to our advantage.
This is blowing my mind. We've got friction, stealing electrons, conduction providing a direct pathway, and induction influencing from afar with grounding as its secret weapon.
Yeah.
It's amazing how these three simple methods explain so much about the world around us.
It really is. Think about it. Static electricity isn't just about getting a shock from a doorknob. It's the same force behind lightning storms, the way your clothes cling together in the dryer, and even how some air purifiers work.
It's like this whole time there's been this invisible world of electrical charges at play, and we're just now getting a glimpse into how it all works.
And we've only scratched the surface here. The research we've been discussing even mentioned things like electrostatic precipitators, which use these charging methods to remove pollutants from industrial emissions.
See, that's why I love these deep dives. We start with something familiar, like a static shock, and end up uncovering a whole universe of hidden connections and mind-blowing applications.
It really shows you that even the most everyday occurrences can hold incredible depths of scientific wonder.
So next time you're dealing with static cling, or maybe braving a doorknob on a dry day, take a moment to think about those trillions of electrons on the move. It's a reminder that there's always more to discover if you just know where to look, or, in this case, what to feel.
And if this deep dive has sparked your curiosity, there's a whole world of fascinating research out there waiting to be explored.
Until next time, stay curious and keep those electrons in check.